Hi, good morning, class. Welcome back to our lectures on quantum field theory, and this is chapter 10 on electroweak theory. This is also known as the GWS model or the Glashow-Weinberg-Salam model or theory. By the way, in parallel to this lecture, please read the books of Michio Kaku, F. Mandel and G. Shaw, and also of Gross's book on quantum field theory. So this is part 1 of the lecture. So this is electroweak theory, and by the way, electroweak is a combination of the electromagnetic and weak interactions of the standard model, and the gauge group that represent this theory is SU2 cross U1. This one here. So the weak interactions is so similar to the electromagnetic interaction, except that for the electromagnetic interaction you have a mediator that is massless, that's the photon. But in SU2 your mediating particles are massive, and these are the positive and negative W bosons and the Z boson. They behave like the photon, but they're massive, and they are only exchanged at short range, which is very unlike the photon, which it can be exchanged even at very large distances. As I have said earlier, the theory that describes the electroweak interaction is known as the Weinberg-Salam model, which is named after Salam, the former director of the International Research Center for Theoretical Physics, and of course German scientist Weinberg and Sheldon Glashow. They won Nobel Prize for the development of this theory, and of course for the prediction of the masses of the gauge bosons or the interacting particles of the theory. In this theory, the Higgs field was introduced so that there will be a spontaneous symmetry breaking, and this SSB actually led to the masses of electron, mu1 and tau, and then the Higgs mechanism on the other hand also generated the masses of the gauge bosons W and Z. There are two W's, positive and negative. However, the photon stays massless. The results of the theory is in good agreement with the experiment in high energy physics experiment, but the Weinberg-Salam model also predicted that the neutrinos would be massless. However, there are experimental results that indicate that neutrinos do have small masses. However, it's really very very small, less than 1 electron volt. And physicists, high energy physicists, particle physicists, are currently doing intensive experiment on this problem, because these may lead to new physics beyond the standard model. And it's even believed that it could be a pathway to solve the long-standing solar neutrino deficit. So here we will be discussing only about leptonic interactions. We will not discuss about hadrons. So we start with the spinors. So we write a Dirac spinner as a two-component object, with the top component being the right-handed spinner and the lower component as a left-handed spinner. So there are 4 elements in this particular column matrix. So you have 2 for the right-handed and 2 for the left-handed. The left and the right-handed components of the Dirac field can be picked out by using an operator composed of the identity and the gamma 5 matrix. Of course, this is a 4 by 4 matrix because you have a 4 component column matrix. But this can be reduced to a 2 by 2 matrix if you only use the Dirac spinner, 2 component Dirac spinner. So this is the gamma 5, and you can use it to pick only the left-handed component. For example, if you use this identity, or you use this expression here, so if you multiply this to the Dirac spinner, you can only extract the left handed component. And similarly, you can also extract the right-handed component if you use this one here, this expression. By the way, this is to pick out the left-handed ones, and this is to pick out the right-handed ones. So you can see from here that the Dirac spinner for the leptonic particles can be written into separately into two spinners containing only the right-handed leptons, and the other one containing only the left-handed leptons. This one here. Now we set up a massless Dirac Lagrangian, and we begin with the standard Dirac Lagrangian and setting the mass term to 0. And this is now our form of the Lagrangian. So this is just your Lagrangian equal to I psi bar gamma mu derivative of psi with respect to mu. Here your psi bar is just written as your psi adjoint gamma 0, as you may have recalled in chapter 1 of this particular lecture, or maybe chapter 2. And anyway, if you put in the left-handed and the right-handed parts of the spinner, then you would expand, be able to expand the Lagrangian into this is like three terms. So you start with that, and then you replace your psi bar with this one, and your psi with this one, and then you'll come up with a very long Lagrangian here. You have three terms. So in that particular expanded Lagrangian, the last term will actually vanish, because if you replace the expression of psi L with this and your psi R with this one, so you will just come up with 0, because this is just an identity, this one. So an identity minus identity is equal to 0. So the last term, these two terms here is 0, and this one is also 0. So the mixed terms vanish. So what is left now is only the first two terms here. So the Lagrangian separates into the left and right-handed components only. So in the case of the electroweak theory, there is an asymmetry between left and right-handed weak interactions. As a result, the actual Lagrangian used will reflect this. This is also in conjunction with the experiments. So again, basing on the standard model, fundamental particles belong to one of three families, and this is not yet explained so well in the standard model as to why there are three families. The distinction for each family is categorized by masses. So the heavier the mass, the lighter the mass, the lightest mass belongs to the first generation, and then you have the second generation. It is now the electron becomes tau there, and for the third generation you have the mu1, the heaviest. The second would be tau, and the third would be mu1. The third would be tau, and mu1 would be the second generation. So they only differ in the masses. Electrons are very light, mu1 are then heavy, and then the tau would be the heaviest. They have the same charge and the same spin. So when you only consider leptons, you can consider only the interactions of the electric interactions of the electron. Then you know the things for mu1 and tau. So each of these leptons, electron, mu1 and tau, they have corresponding neutrinos. So that's also That's also corresponding to the leptons. So all in all, the Lagrangian would have to be written here. It's supposed to be the sum of the Lagrangian of the electron, the Lagrangian of the muon, and the Lagrangian of tau. And so these are all similar, only the masses are different. So you can only study electron and then you know of what for muon and tau. So there's a question. So what is with the other two families? So some physicists, some particle physicists, they try to search or explore string theory to explain these things. The electron field and its associated neutrino are combined together into a two-component object. So the upper one would be the neutrino and the lower one would be the electron field, and they're the left-handed. So since the electron neutrino is massless, then the spinor for the right-handed leptons would be having zero component on the upper corner, and for the lower corner you have a right-handed electron. So again, the left-handed spinor is this one. And so anyway, your left-handed electron fields are related in the way that we relate left-handed psi. So you will just have to multiply 1 minus gamma 5 divided by 2 to the electron field, and you will get the left-handed electron. And then for the right-handed electron, you just multiply 1 plus gamma 5 divided by 2 if you want to get the right-handed electrons. So again, if the mass of the neutrino is taken to be 0, then there's only a left-handed component of the neutrino field, because being massless, you cannot change its handedness. So your left-handed neutrino satisfy this, and we just don't use the notation L, we just leave it that way. Just we have to understand that it's just entirely left-handed. And so now for the right-handed component of the neutrino, you have 0, and so your right-handed field, Dirac field, would be only this. So we can now substitute this psi L and psi R to our Lagrangian. By the way, this Lagrangian is only for the electrons, but if you would add mu1 and tau to the full Lagrangian, it's just duplication for the electron. So for simplicity's sake, we'll just consider electrons, and later on we'll just add the mu1s and tau. Anyway, the difference would just be the masses. Everything would be the same. Spin and charge would be the same. They're just identical in form. Now we will go to the charges of the electroweak interaction. So charged currents coupled to the left-handed particles and to the right-handed particles. And in electroweak theory, there exist three types of charge. One is electric charge, the other one is weak isospin, and the other one is the hypercharge or the weak hypercharge. And these are related by the Gell-Mann-Nishijima relation, which is just given by Q equal to I3 plus Y over 2. I3, not IQ. I3 is the third component of the weak isospin. So for a neutrino, the weak isospin is just 1/2, or that's the I3, the third component of the weak isospin. But anyway, the electric charge is related to the sum of the weak isospin, the third component of the weak isospin, plus 1/2 of the hypercharge. Now this is the assignment. The neutrino is assigned an isospin of weak isospin of I3 equal to 1/2, while the left-handed electron has an I3 of negative 1/2. So this is actually not I3 nu but I3e. I'm talking about this one. And the right-handed electron field has IR equal to 0. And for the left-handed spinor, Y is equal to negative 1, while for the right-handed spinor, Y is equal to negative 2. Hence, overall, the charges of the left and right-handed spinors in the electroweak theory are this one. So you have for the neutrino, this is the charge for the neutrino is 0, so you will have I3 would be 1/2 plus 1/2 of the hypercharge of negative 1, so that becomes 0. For the electron, you will have an I3 of negative 1/2, and then you add 1/2 of negative 1, then you would have the total charge of the electron to be equal to negative 1. And for the right-handed electron, you have a weak isospin of 0 plus 1/2 of the hypercharge of negative 2, and again it results to a charge of negative 1. The weak hypercharge Y and weak isospin charge I are independent, so you will have a commutation relation that equates to 0 for hypercharge and isospin. By the way, please note that there are 4 gauge fields for electroweak theory. You have W mu1, W mu2, W mu3, and the other one is B mu, which correspond to the weak isospin charge I and weak hypercharge Y respectively. So if a particle has a given type of charge, then it can interact with the field associated with that charge, and the value of the charge determines the strength of the interaction. So if you have a charge of negative 1, and of course it will interact with other charged particles, twice the amount as that of a charge that has only a charge of a half, for example. So in any case, the neutrino has a charge 0, so it does not participate in electromagnetic interaction. It participates in weak interactions, however, it cannot be, of course, detected by electromagnetic detectors. So detectors that detects charged particles cannot detect neutrino particles. So again, it has quantum numbers of I3 equal to 1/2 and weak hypercharge equal to -1, and of course it results to an electrical charge of 0. A left-handed electron participates in the weak interaction and also interacts with the photon, and all of its charges, weak isospin, weak hypercharge, and its electrical charge are all non-zero. The right-handed electron, however, has a weak isospin of 0, and it has a weak hypercharge of -2 and a total charge of -1. The isospin charge allows a particle to interact with the gauge bosons W mu. So in this case, the right-handed electron does not interact with the gauge field, only the left-handed ones. However, it will interact with the photon field, or the B mu, because it has a charge of Q equal to -1. But in fact, it does interact with twice the strength of the left-handed electron because of the hypercharge, the quantum number hypercharge, -2. Now let's look at the unitary transformations of the Dirac fields, and of course the gauge fields. And in here we will consider the possible symmetries of the theory and proceed to introduce the gauge bosons. So again, electroweak theory has two independent symmetries, SU2 and U1, and they are combined here in this group, SU2 cross U1. And in SU2, again, there are three gauge bosons, W mu1, W mu2, and W mu3. And we will find out later that W mu1 and W mu2 just represents the positive and negative W bosons, while W mu3 is just the Z boson. So the conservation of the weak hypercharge actually arises from the invariance of the Lagrangian under the U1 transformation, and hence there is an additional gauge field associated with U1 invariance, and this is just denoted by B mu. So there are four fields in electroweak theory. The other three are massive, and the other one, the one that remains massless, is just the photon. So after introducing the gauge fields, the Lagrangian now becomes a Lagrangian that is the sum of the leptons plus the gauge field. By the way, leptons again is expanded into three identical parts except that they have different masses. L lepton is a combination of the Lagrangian of the electrons, the muons, and the tau. Now going back, let's consider the mu1 transformation. And it is clear that by looking at the Lagrangian, it is invariant under a standard U1 transformation for the right-handed spinner here. So for this U1 transformation of the right-handed spinner, the transformation remains the same. With the transformation, the Lagrangian remains the same. So you can replace your psi r with this one and this one. By the way, your psi bar r, your psi bar will just be equal to psi r bar f exponential of negative I beta, the conjugate, just the conjugate. So your L prime is just equal to your Lagrangian, original Lagrangian after the transformation. So clearly the Lagrangian is invariant under the transformation of the right-handed leptons. Now, however, the U1 transformation is not invariant under the transformation of the left-handed component of the leptons. Why? Because you have this transformation, and the left and the right-handed fields have different weak hypercharge. So their transformation are expectedly different. So this is the correct transformation of the left-handed field here. This is due to the difference weak hypercharges between the two kinds of leptons. So since YR is -2 and YL is -1, the left-handed field interacts at half the strength. So you will have to add an N that is equal to 1/2 in the transformation. So therefore, our correct transformation is not psi L prime equal to exponential of I beta psi L, but it's actually equal to exponential of I beta over 2 psi L. So we can now arrange in one spinner, one Dirac spinner, both the left-handed components and the right-handed, with of course the left-handed being composed of the new and the the electron fields, left-handed. So you will have nu E, EL, and ER in one column. So how do we transform this? So you will have your column matrix written in this form, and then you will transform it into prime. The transformation is the prime. So you will have this column matrix here where you put the prime in each field, and so the transformation factor would be or could be written into a matrix 3x3 matrix form here, where the two diagonals, the first two diagonals would be exponential of I beta over 2 because of the weak hypercharge of -1. Now, with a given gauge field d mu, we define a field strength tensor F mu nu, where again, as usual, it is defined as F mu nu equal to the derivative of B mu with respect to mu minus derivative of B mu with respect to nu, just like we did in electromagnetism or QED, quantum electrodynamics. So the gauge field B mu is included in the Lagrangian. We can add this term to the previous Lagrangian that we know in order to have a generalized SU2 cross U1 Lagrangian. So you will have again, this is the definition of F mu nu, and this is the form of the Lagrangian. This is the kinetic term of B mu. This is to preserve the action under the variation of the action. That means your change in your action would be 0. So just like in QED, the gauge field B mu introduces extra terms into the derivative in order to maintain covariance, and you can only do it. The invariance could come out if you change the derivative into a covariant derivative by adding this term. So you will have you will change the derivative into a covariant derivative. That's just the ordinary derivative added with this term. By the way, the GB here is just a coupling constant associated with the gauge field B mu. And of course, when we do the gauge fields W mu 1, 2, 3, of course they will have different strength compared to the B mu. So we will denote it with another G. Now, since we consider SU2 transformation, we reintroduce the Pauli matrix in anticipation of SU2. So our Pauli matrices are again given by tau. These are the generators of the SU2 matrix. So you have this one here, 0 1 1 0, and then you have a generator of 0 negative I 0, and then the other one is a 1 0 0 negative 1. And the Lie algebra for these generators is given by this. This is the commutation relation of the three generators. By the way, the tau I here are generators of associated with the weak isospin space. So by the way, your epsilon ijk here would be equal to 1 for cyclic permutations of ijk, and for the non-cyclic permutations of ijk you have epsilon equal to -1, and they will be 0 when the indices repeat. So say for example epsilon 1 1 1 1 2 for example is 0, or epsilon 3 2 3 is also 0. So only the cyclic arrangements where the three indices are not the same is equal to 1, and I mean the epsilon. So when you have an epsilon that's say for example epsilon 2 3 1, this is equal to 1 positive, because this is cyclic. You have 2 3 1, and then epsilon 1 3 2, this is not cyclic, this is -1. The cyclic is supposed to be epsilon 1 2 3. This is equal to +1. Now we use them to consider an SU2 transformation of the form here. U alpha as an exponential of I alpha j tau j over 2. So for this given transformation, SU2 transformation, your psi r, or right-handed Dirac field, would be just the same because it has a 0 upper component. However, the left-handed spinor transform in the same way, but it is not equal to psi l. Since of course the right-handed electron ER do not carry any weak isospin. So in that case, it does not couple to the W mu1 field, W mu2 field, and W mu3 fields. So our transformation matrix for SU2 can be reduced to this 3x3 matrix. You have the first diagonal as this, and this one for the first two, and the last one you can write it as 1 because your right-handed Dirac spinners are invariant in that transformation. Now, consider the field strength tensor corresponding to the three three gauge fields W mu 1, 2, 3, and so we will have a form of the F mu nu L as this one here. This has three components. This is because our mu W also interact with themselves. And of course there are three of these in the SU2 group, while in your U1 group you only have one. You only have B mu. Now since we have three gauge fields, we then add the field tensor to the Lagrangian by summing up F mu nu L F L mu nu over L 1, 2, 3. That's to include the three gauge fields W mu 1, W mu 2, and W mu 3. And we take the trace of the matrix and then we add it to the Lagrangian, and we term it as LW, which is just negative 1/8 times the trace of F mu nu F mu nu in this expression. Again, to keep the derivative covariant, an exotherm must be added to account for the presence of the three fields in the Lagrangian, and this is done by adding the following terms to the derivative here. Now, since the right-handed lepton field does not participate in the interaction involving the weak isospin, you cannot add the term, the derivative term in this case. So you can only add the term to account for the presence of the gauge field, and so you can only add this one. This one, and for the left-handed you have this one. So altogether the total leptonic portion of the Lagrangian is now this extended form here. So the total Lagrangian, now including the gauge field Lagrangian, would be this. We now include also the U1. This is now representing SU2 cross U1 Lagrangian. SU2 cross U1. All of these things here. So here your F mu nu the small letter f there, as is associated with the b mu, while your capital F mu are associated with the three massive gauge fields. So looking at this Lagrangian, there is an asymmetry between the chiral fields, and of course standard model is experimentally successful. They have a good agreement, but it also leaves a lot of problems, a lot of questions that theoretical physicists need to answer, needs to solve. But it's, of course, that is beyond the standard model. It could be answered by supersymmetry or string theory, or higher dimension, or even the GUT theory or grand unification theory. For the next part of the lecture, we'll be discussing about weak mixing angle, or the Weinberg angle, and of course we will see how the Higgs fields are introduced to the theory and how it's able to generate the mass of the gauge fields, or the particles associated with the gauge fields. So that's it for the part 1 of the lecture. We will continue with the lecture in the next meeting.